Hey everyone, welcome to the second part of our little mini polymer unit. Last time we talked about chain growth mechanisms of polymerization. Today we're going to talk about the other part of that, which is step growth. So they're kind of the two different umbrellas under which we have a whole bunch of different types of polymers. So what the heck is step growth? I feel like it's not maybe not the best name for what is actually happening in this reaction, but let's try to put some definitions and some terms into this step growth. So if you have a polymer that grows by step growth, it means that it can react in multiple different directions all at the same time. And so that is to say that there's no single growth direction for a polymer at any given time. That was definitely the case in chain growth, and we'll look at some examples in a moment, where we have one unit that's polymerizing at a time, and then we just add single additional units onto that in succession. But here, we can be growing in multiple different directions in sort of multiple ways all at the same time. So it's not necessarily that it's more random, it just is happening in a very different way, right? This could be adding multiple pieces on in different directions all at the same time. So what does that kind of look like? Let's compare this to the chain growth that we were just mentioning. So here's something, this could be like a polystyrene kind of a radical reaction. So I've got here this radical electron, right? And for this polymer chain that we're going to start growing, that's the only spot we can react, right? At that one radical electron. So then we will go ahead and add one more unit to that, and it will start to look something like this right here, where here's our same previous unit that we started with. That's like the first one. And then we're adding units onto it, as I said, in succession every time. And that gives us a very distinct direction of growth because we have to add the, so this is unit one. Every time we have to add the second unit to it in this direction. And we have to add units 3 and 4 also in this direction, right? There's no way to go the other direction. That doesn't work because there's nothing there that we can react with. So in contrast, your step growth is going to look a bit different. It's going to look more like some kind of a molecule. So these here are obviously just cartoons, squares, triangles, that kind of thing. But we're going to have multiple places at which we can react. So I'm going to designate this, instead of with a radical like we did here, right? This red radical that I'm highlighting is the only place we can react. In red over here, I'm going to draw in the places that we can react in a step growth type mechanism. So this is going to be very vague, right? But we're going to have some kind of a group G that exists at multiple places on the same monomer unit, right? So I'm just going to label these G4 group. We'll talk more about what those groups are in a moment. But depending on what your molecule looks like, we're going to have at least a couple of different G groups, or they could be the same G group, that allow a growth in that direction. So if we look at this simplest one down here at the bottom, we have two different G groups. So we could polymerize in this direction, or we could polymerize in this direction. So what that might look like would be for us to take this same square unit and say, oh yeah, okay, that's going to react at this direction, but it can also react in this direction at the same time. So our original square number 1 could be there, and then this could be 2, and this could be like 2 prime, right? Because who knows, maybe they reacted at the same time. Point being that we can react in this direction and in that direction. Same thing with these other 2 examples above. Again, these are just generic cartoon examples, but we can grow out in these 3 directions for this triangular one, or we can grow out in 4 different directions. If you have that many groups attached, you have a lot of different possibilities. So another way to illustrate this is with a sort of series of, kind of cartoon pictures of what a step growth reaction might look like. So let's take a look at this courtesy of polymerdatabase.com. They have this sort of cartoon way of looking at things. We have these black circles here, and then we have these empty or white circles, and they need to react together. So what we're going to say is that the black circles have some particular kind of functional group on them. Let's draw out like a pretend little G here for a minute. And the white circles have some other group on them. We could call that R. But the point is that the black circles must react with the white circles, and the white circles must react with the black circles. And it doesn't really matter what those groups are, G or R. But what's going to happen is that in a single step, you're going to have some of these that are just close enough together react, right? So here we have a new bond between black and white, and same here. And then, this piece, say maybe it got kind of two at once, right? It's a little bit less, like I said, controlled as far as you don't know exactly what's going to react with what. It's a little bit random. So some of them start to kind of get hooked together and start to make, if there are two units together, we would call that a dimer or a trimer if there are three. So starting to make small molecules by connecting a couple of them together at a time. And then as we go along, you'll start to see those chains, right? Maybe we can highlight this one particularly in red, ends up being essentially the same thing here, right? Where that sort of 3-unit piece is now building on and getting more pieces to it. And if we follow this through all the way to the last one, at some point, eventually, you make these chains that could be really long chains. You do also have some, you can see here, this little one kind of got left out. It didn't, all the other ones around it got used up. So maybe they're shorter, maybe they're longer. It's going to give the polymers just different properties. And that's good or bad depending on what it is you're trying to do. So that's the idea here, is that we're kind of reacting in these different steps. So like I say, step may not be the best name for this type of growth. If you have a better name suggestion, let me know. I don't know if they'll go for it, but I would be curious to see what you think is a better term to describe this, because I'm still struggling to come up with one for myself. Okay, so we've looked at this. Hopefully you've got some idea of what these step growth polymers are doing, but it's also, it's been kind of vague a little bit. It's just cartoony. Basically, all we've seen so far are cartoons, and that's not really what polymers look like. So let's look at some actual polymers to get a better idea. What you're going to be asked to do for this half of this polymer unit is just to think about identifying which one is a step growth polymer compared to a chain growth polymer. Now, that doesn't mean you're going to have to memorize a bunch of these polymers. What you'll be looking for is this characteristic here that we're going to fill in right now. If we have at least two identical functional groups that are attached to the same molecule in a polymerization reaction, that's going to be a step growth polymerization. So what do I mean when I say functional groups? You may or may not have heard me use that term before. That is our G, right? Sorry, that looks like a 6. Let me redraw that so it looks like a G. Nope. One more time. There we go. So that G, or functional group, is just some kind of a chemical pattern, right? So we'll talk about some of the different chemical patterns that are the functional groups for these types of polymers, but there are so many. And that's why I'm not going to ask you to memorize them all. I just want you to be able to look for this sort of double-ended, or maybe it's a triple or quadruple motif, so that if you see that, you know, oh, okay, that definitely has to be a step growth polymerization reaction. So here's an example that y'all probably have heard of before, nylon. So nylon happens to be a copolymer of 2 different units. Most of the examples that you're going to see today of step growth polymers are copolymers that consist of 2 different units reacting together. That's not always the case, but that's maybe some of the most common examples. So that's the theme we're going to fit in today. So nylon takes this kind of chlorine bonded to this C double bond O. That's kind of one functional group. That's one chemical pattern or motif that we're going to react with the other chemical pattern here, which is NH2. Those are amines. You probably did hear us talk about that during the nomenclature portion of Unit 1. So what you should know is that when we take this sort of purple highlighted piece here that has those 2 nitrogen-based groups at the end, these are the G functional groups that you are thinking about when you're trying to identify these. If we take that and put that with this piece that has those chlorine and C double bond O pieces, if we put those together, we get this other thing over here, and that's the polymer. So if we kind of think about which carbons are where, you don't have to number them all out if you don't want to, but thinking about these C double bond O groups are here. So this piece is our orange piece. And then the nitrogen piece has to, of course, that keeps the nitrogens that it started with. So that ends up there. And then this repeats on and on and on. So that's what this little squiggly line here shows. And I forgot to draw one over here. It just means that this keeps going and going and going, basically infinitely. You might also see in the book, or I may write it in our notes, that there sometimes will be a little lowercase n near the bottom of a polymer to show that that repeats some integer n number of times, and that it's not just this many atoms, it goes on and on and on. Again, you don't have to worry about too much of the specifics of how to draw this and the nomenclature of polymers. You should just know that, okay, I can see that we have these two different pieces that each have a functional group on two ends of the molecule, and they're reacting together. That's what constitutes a step growth polymer. And so this is what we call nylon. This specifically is nylon 6,6. There are multiple different types of nylon. And again, don't worry about that nomenclature, what those sixes mean. But the more broad and general category here is that this is a polyamide. And again, you don't need to know the name amide specifically, but just so that you know, it is this piece right here. When we have a nitrogen that is singly bonded to a carbon, which is doubly bonded to an oxygen. And you may also already, given that you probably have heard of nylon, you may already have some ideas about what nylon is and what that is for. It's definitely in clothes. In fact, the kind of tights that some people like to wear are literally called nylons, but that's what they're made out of. They're made out of this polymer named nylon. You may also see it in things like rope for a variety of different applications, but like mountaineering rope. It's also in fishing line. So if you're out there on Kentucky Lake doing some fishing, you're using nylon, you're using chemistry. So that is one example. Let's look at a couple of other examples that are going to be step growth polymerizations. So this one is called Dacron. And I had never really even heard of Dacron, but when you hear the more polymer focused name, it'll probably ring more of a bell. So on this one, we have some slightly different functional groups to contend with here. So we have kind of this piece here with the C double bond O, and then that's bonded to an oxygen by a single bond, and then there's some carbons here. So same thing on this side. So those are kind of our blue pieces, and then there's something that connects them in the middle, like so. And then we've got this other smaller piece here, this just sort of 2 carbon with 2 oxygens on it. That's actually ethylene glycol, which is in like antifreeze. So when we take these two, combine them together, we get this, again, copolymer. It looks like this. We have our kind of blue piece here with those double bond and then single bond to oxygen functional groups. And then they actually kind of sort of overlap here a little bit, like this oxygen. We're not really sure. That could come from one or the other. It happens to come from the red one, but you don't need to know that. We won't be doing any of the mechanisms for these, so you don't have to worry about mechanistically how did we get to one place or the other. So what we've built here in the middle, this thing with both of those oxygens contained together, is what we call an ester functional group. And so the polymer itself is named a polyester, which if you've ever looked at the label on any of your clothes, you probably own something that's made out of polyester. And it may or may not be this exact polyester. There are many, many different ways to make a polyester. This one is just one particular example. So Dacron, again, not a name that I had really heard of, but it is in clothing. And the other thing that you might have heard of, this is the only piece that rung a bell for me, is Mylar. So I think that's another trade name, but Mylar is like the stuff, if you ever have like not like a rubbery balloon, but those like kind of foil balloons, like it's a star shape, I think in the picture in your book, or if it's like a balloon of, you know, SpongeBob SquarePants or whatever. They're kind of like have a foily texture to them, but they're not aluminum foil, they're this Mylar. So they're kind of like plastic with some kind of shiny coating on them to make them look kind of like they are foil. And I'm sure there's a lot of other applications for this other than just clothing and balloons, but if you're curious, you should do some looking on your own. Another example here is Lycra, and that name may ring a bell to some of you. So again, just looking at our sort of functional groups here, we have this kind of funny looking thing here, like standing up with 2 goalpost arms. Essentially, we have this nitrogen double bonded to a carbon, which is double bonded to an oxygen. That's a slightly strange functional group, but you may see it every once in a while. So we have that kind of green unit here. And then again, we have the same ethylene glycol here. That's just a a random chance. It's a useful thing to make polymers out of because, like we said, it has those two identical ends to it. It has the same functional group repeated on it twice. And then if we look at the polymer that it makes, another copolymer, here we have these pieces coming from our first molecule there, the kind of carbon and oxygen. We've changed it around. I'll put a little label in here because it may be a little bit weird to think about. These red starred carbons become these CO carbons there. We're changing around some of the bond structure. Again, you don't need to worry about mechanistically how that happens. And then here's that oxygen. Oops, wrong tool. Here's that oxygen from ethylene glycol coming in there. So what is the functional group that we've made here? This is kind of a weird one, even for me. We don't use these. They're not super common in regular organic chemistry. That piece there, the nitrogen bonded to the C double bond O with another O on the other side of it, is a urethane. So this one is a polyurethane. And again, that might ring a bell, maybe not so much as the name lycra does, because lycra is a much easier and nicer sounding word. But polyurethane is in a couple of pretty important things. So the thing that I always think about it in conjunction with is something like furniture cushions. If you make this polyurethane polymer and you do it in the presence of like a bubbling gas, essentially you make a foam. And that foam is polyurethane, so it's probably what is in your couch, you know, in the dorm or at home. And then lycra also, you probably would have heard in conjunction with clothing, because I think that's the sort of brand, one of the brand names that is synonymous with spandex. And for my part, I was a rower when I was in high school and undergrad, so there was a lot of spandex. For those folks who like your comfortable athleisure leggings, or if you like your compression shorts or your Under Armour tees, if you're into that kind of sporty outerwear, innerwear, wherever you want to wear it, most of it is spandex. So you're wearing a polymer every day. So really what we're practicing doing is just looking at these functional groups that are kind of on either end of our molecules. Again, you don't need to know what their names are. You just want to be able to identify, oh, that has two like functional groups all together. That means that this can react to make a copolymer in a step growth fashion. So if you have any questions about this, please do let me know. I have one last example for you that I basically have to put in here because it's my favorite example. It's something that I worked on during my PhD, which you guys don't need to know anything about, so I'll make this really quick. We have this big, crazy honking molecule. Please don't write this down in your notes unless you really, really want to, because you will not be asked anything about it. This is called a phthalocyanine, and there's some metal atom in the middle there. We take that, it has this special functional group of a diol or a dialcohol, where they're right next to each other. And then we take this kind of weird looking thing with boron on it. I'm one of the very few people who cares at all about boron because it's kind of a weird element. But what we use it to do is to do a copolymerization reaction to make a crazy thing that looks like this. Now this is wild, right? This is the kind of example of that square that we looked at earlier that could have 4 different reaction points. And so that's what happens is we make 4 different connections to this small molecule here with the boron on it. And that gives us kind of this square-shaped pore, and it basically makes, if you zoom way out, a big grid with empty holes that you can put stuff into. So the functional group that we've made here is a boronate ester. And we've made a whole bunch of them, so you could call this a polyboronate ester. But most people call these COFs, or COF, which stands for covalent organic framework. So now it's not just a single line of a polymer that can kind of make strands, right, and fibers. A lot of this, obviously, as you heard, was used in clothing. Now this makes almost like a honeycomb framework. It's 2-dimensional, right? So these are used for some very different things, and they're definitely not a big market-ready thing like all the rest of the polymers that we've looked at so far. But they can be used for things like solar cells. They can help pick up light and convert it into energy. They can also be used for things like water purification and filtration. And that metal that sits in the middle there can also be used as a catalyst, which is a little bit of a niche thing because really only chemists are going to be interested in purchasing catalysts, but they have a lot of cool properties. If you're interested at all in this, or you know somebody else who might be, you can send them my way or shoot me an email. Anyway, enough about that. Let's talk about some problems, because you know me, I'm very biased and I love polymers a lot, but I would be really remiss to not turn a critical eye to them and just think that they're perfect, right? Because we think of polymers as this perfect packaging. At least I typically think about it that way, but it's got some problems. It perplexes me, to say the least. So let's think about some pros and cons about plastics and packaging. So some of these you may already know, some of them you may not be aware of, and that's why I want to bring them up. Some of the pros include that plastic is very lightweight. If it's light, that's good. That means we need to use less energy and therefore gasoline and therefore CO2 emissions to ship things, right? Because they're less heavy. It's cheap. It's readily available. And if it's cheap, people are going to want to use it. It's easy to make. We can have a lot of it without costing us too much money. One of the other things that's important is that it can be used for sanitary needs or being sterile. There's certain things that you want to make sure are sterile, right? So think about surgical implements, right? If they're single-use type surgical implements, or even like single-use, toothpicks at a restaurant, right? We often find those wrapped in plastic because we want them to be sterile and safe and not covered in germs, right? The other pro that I could think of while I was just coming up with a few is that they help keep things fresh. So sometimes that's a concern for like, I don't know, physical household items that you would buy, but more so this is about food, right? If we can keep food fresh longer, that means less food waste, which is also a big problem. So those are some things that plastics are really great for, right? And we want those things, particularly thinking about food waste, trying to avoid that, and how to keep things sanitary and sterile are really important innovations that have allowed us to come as far as we have as human beings. But there are some cons, right? Recycling is a con, unfortunately. So there are many problems with recycling, and I'm by no means an expert on all of them, but recycling is the kind of thing that you can only do 1 to 3 times. And then a lot of the plastics are not useful anymore. They've degraded and not become as reliable, right? They may not hold up as strongly as the first time they were recycled. So it's just not exactly good from a materials standpoint. The other standpoint that recycling is a con for is the cost. You'll notice how I put this one directly across from cheap. It's really cheap to make a fresh batch of polymer, whereas recycling involves the collection, the cleaning, the removing of labels, the melting down of the plastics, and then remolding them. It costs all of that when we could just make a fresh batch really, really cheap. So the cost of recycling is high. That means nobody wants to do it because there's just not enough money in it. Another concern is ocean and land accumulation of polymers. If we are just throwing away plastics and polymers, and sometimes they get to the landfill, but sometimes they don't. And even if they're in the landfill, they're mostly going to just sit there. They don't really degrade naturally in the environment, at least not over the course of tens of years, hundreds of years. It could be thousands of years that these materials will still be sitting there. And so if they're accumulating in the water and the soil, partly this is just sort of an aesthetic thing that do you want to live in a place that just has trash everywhere? I sure don't. It doesn't look good. It feels bad and it's not natural to the environment. That leads into this other con about microplastics. So microplastics, really, that's relatively new. We've found that these plastics that are in the environment are, starting to degrade, or maybe they're just getting, pushed around by waves and crashing into each other and breaking apart into smaller and smaller pieces, so small that they are becoming microplastics. And we don't really have a good understanding yet of what effects these microplastics have on our ecosystem, on our health and wellness, because they're getting into our water, they're getting into our food, and that means they're getting into us. And I think that's scary. It may or may not be a bad thing. We just don't know yet. So we have not really a good idea or understanding of what the effects might be. And in that way, we can't really do anything about them. So we've got some pros, we've got some cons. This is not an exhaustive list by any means, but I just pulled out a few that are forefront of my mind. And so what I just want to wrap this slide up with is to ask you what you're thinking about with this. What do you think? Are the pros good enough or the cons bad enough? Where do you stand? Whether you feel like you're a chemist or not, you are surrounded by polymers constantly. They have an effect on you, the place you live, your body, your loved ones. So they are your problem. And I want you to consider where you stand on polymers and come up with an opinion. Furthermore, what do you believe needs to be done? We're going to have to make a choice. And one of those choices may be to do nothing. That may be the better choice. The other choice is that we might have to do something. And what that something is, well, we don't know. We're going to have to figure that out. There may be a bunch of different things that we can try all together. We need to critically think to find whatever the best solution is going to be. So I just want to reiterate that even if you try never to think about chemistry again after you get through this class, that's fine with me. But know that it is all around us and affecting us in different ways. So I just want to encourage you, even if you try never to think about chemistry ever again after you're done with this class, it's fine. I won't blame you. But I do want you to sort of think about these questions, right? And keep them in mind. I want to encourage you to be better than I was when I was your age. And I just kind of didn't think about things and I didn't really care. And if you care about something, I want you to take action based on that and make the world what you want it to be, right? So that's my little soapbox about thinking about the pros and cons of things and trying to find a place to stand, right? I love chemistry so much more than you guys will, I'm sure, but it is a double-edged sword. And that's probably true of a lot of the things that you may be thinking about for your future career, things that you're studying. So I'm going to encourage you to, you're going to hate this, take a critical thinking lens to whatever it is you're working on, right? Think about the pros and the cons and just try to make informed decisions. Okay, so let's just look at one last example here. This is a chemistry-based solution, or I should call this a potential solution, because it could work, but it may not be the only solution. It may not be the best solution. So this is a potential solution. Thinking about how plastics have some of these cons, right? That we are worried that they might hurt, the environment or nature. We don't want to do that. At least I don't. I love nature and I want it to be as healthy as possible. So one thought there is, what if we make the plastics from things that are in nature? And so an example of that is this PLA polymer, and that stands for polylactic acid. So y'all may have heard of lactic acid before. That's related to sore muscles after you've been exercising. So lactic acid is a naturally occurring compound. A lot of the other examples that you've seen today are not necessarily derived from nature. They're often derived from petroleum feedstocks, which means that they're not necessarily renewable. Something like a lactic acid, though, is found in nature, it's found in us. So therefore that gives us the idea that maybe it would not be as detrimental when it goes back into nature, right? Because we kind of don't have any way around that. It's going to happen. So what if we just plan for that ahead of time? So what you're looking at here, this is not exactly lactic acid. This is a dimer of lactic acid, which means there's two lactic acids put together to form this kind of ring shape. And then if we do a step growth style polymerization of this, we can turn it into this polymer polylactic acid. Again, don't worry mechanistically about how this happens. So this might look a little bit different from all the copolymer examples we looked at earlier. This is a single monomer type polymer, right? So there is no second component here. It's just the lactic acid, right? So one of those sort of units is here, and the other unit is here stuck together. And then basically what you do is you just open up this ring and unfold it, and that makes this chain where we have these C double bond O's and then some O's that are stuck in the chain here. And so here are those units again in the polymer. You've got one kind of here and one kind of there, and they just repeat over and over and over again. So you may not have heard of polylactic acid, but you may have actually used it. What you would most commonly find it in are things like single-use plastic cups. Normally they're clear and they often have like a green label on them to kind of say, oh, hey, look, this is environmentally friendly, it's green. And so these plastic cups are meant to be single-use plastics that get thrown away. And so the idea being that if we have designed ahead of time to think about the end of life of a material, we can kind of plan for what's going to happen. A disposable cup is meant to just be thrown away. If we design it so that it will start to break down immediately after it gets thrown away, then hopefully we can foster a decomposition by like composting and having microorganisms come in and start to degrade the material, take it back to lactic acid and things that are even smaller than lactic acid, like maybe CO2 could be a potential byproduct of the degradation of PLA. But ideally, that would be better than, say, styrofoam, right? Because that will just hang around and it cannot be digested by microbes. So that's the idea behind this potential solution, is just using our chemical knowledge to find alternatives that can have similar properties, but hopefully will be a little bit less bad for our environment. So with that, here's some things to think about to review and practice. Looking for what constitutes a step versus a chain growth polymer. You'll have some of that on your homework. We want to be familiar with those two polymerization mechanisms we talked about last time, and also those radical electron terms: initiation, propagation, and termination, and identifying those steps. You'll get a lot of practice with this on your homework. And then this last bit is, obviously optional, but I would encourage you to take a look at your own moral compass, specifically as it relates to polymers. Like I said, you can't really get away from polymers. You can't get away from plastic. It's everywhere. So decide what you feel about plastic, whether you think it's a problem or not, and then back that up with your actions. Speaking of backing things up with your actions, by the time you're watching this, it's probably at least October 5th. I hope you all are registered to vote. Doesn't matter who you vote for, you got to get out and vote. Let me know if you have any questions about how to vote in this area or plastics in general. I'd be happy to talk about either of those. And if this all feels good, start looking ahead to our substitution reactions. That's going to be the big part of the remainder of our unit, and you're going to need to dedicate a lot of time and practice to it. So if you can get a head start on that, that'll be really good. If not, just let me know about any polymer questions you have. You can post a comment here, pop in the discussion forum, stop by office hours, or send me an email. Until then, take care.